Okay, the first thing that you're going to do is see the factored version of this function. It's important to see it factored. It's nice to see it unfactored for certain features, but you really need to see the factored version. So let's take out a GCF first because we have a 4, 16, 16. Oops. And then let's factor this trinomial right here. Okay? So we're going to replace this with what I just wrote. Okay, very important to have the factored version. The next thing is I would recommend you write down your big 5 features, so you don't forget them, because you want to make sure whether or not you have them, the ones that you do get drawn on the graph. Okay, so let's tick through each one and go over the rules. HA, it's about degree, comparing the degrees on the top and the bottom. When it's unfactored, like here, it's very easy to see that degree is heavier on top by 1. But heavier on top means there is none of this. Heavier on top by 1 means there's going to be a slant asymptote. Okay, and we'll come back to that later because we're going to have to calculate this. VA, we are looking in the denominator. VA is where you may not have zeros in the denominator. This is illegal. So that's why we're looking in the denominator. And we can see if x equals -3, you're going to have 0 in the denominator. And by the way, this is the equation of the line. We'll come back to, we're going to draw all these all at once. Whole, you're looking for a factor that's the same in the top and the bottom. Is anything here cancelable? Cancelable means you see the same thing on the top and the bottom, and you don't. So we can say no whole. X-intercept. X-intercept is found in the top. You are allowed to have 0 in the numerator. This is okay. Can you think of any x's that will make any of those factors 0? Well, you have a repeating factor, so there's only one x that you need to calculate that will make both of them 0, which is that's still going to give you an x-intercept, and that is -2. Your x is -2. For all x-intercepts, y is 0, because you're going to plot it right here. That's where your x-intercept is going to be drawn, where y is 0. Y-intercept. Y-intercept, it's convenient to look here. It's doable by looking at this version as well, but it's what happens when you plug 0 in for your denominator, for your 0 in for x, and seeing what comes out. Well, when 0 is plugged in here for x, all that remains is 16 on top and 3 on the bottom. And so that is going to be our y-intercept. It's actually good to turn this into a mixed number, so it's a little bit easier to see where you're going to plot it. I think it's 5 1/3. because 3 goes into 16 5 times, with the remainder of 3, of 1, 1 over 3. Okay, so that's your y-intercept. Okay, the last thing we have to come back to is the slant asymptote. Slant asymptote is found just by doing the division that this fraction represents. Now, there are two ways to do it, at least two. One is synthetic, and synthetic division is allowable because you have a linear factor here, meaning just an x of power of 1, and no coefficient here, or a coefficient of 1. Okay? The one that works all the time is long division. So as long as you know when to use synthetic and when not to, you're fine to do that. But I prefer long division. And you don't have to do that many steps. You don't need the remainder. So x times 4x will make 4x squared. 4x squared comes back. We distribute this to the 3, 12x. But remember, we're subtracting, meaning changing the signs before we take the next step. 16x minus 12x is 4x. I don't need to worry about bringing this down because my next step is all I need. X times what makes 4x? X times 4 makes 4x. And I can stop right here. So here's the equation of our line, right here. So the slant asymptote, which I'll write here, is a linear equation that goes y equals 4x plus 4. Okay, so we have all our features. We know there's no hole, but looks like we have pretty much everything else. So let's go ahead and plot. I'm going to start with a slant asymptote. Now, plotting a line when it's in slope-intercept form, which this is your y-intercept, positive 4. So that's going to be the first point that you plot. Put the y-intercept right here. Remember, this is not the graph. This is just the asymptote. It's where the graph does not touch. But this is your y-intercept. And then this is your slope. And slope is best seen as a fraction so that you can separate out the rise and the run. So 4 becomes 4 over 1. They're both positive. So it's going to, the next point is going to be a rise of 4 and a run in the positive direction of 1. So let's plot that. From the y-intercept, 1, 2, 3, 4, and then our next point. Now let's do it backwards. Backwards run, 1, 2, 3, 4, backwards rise. And we see if we just continue that pattern, 1, 1, 2, 3, 4, 1, 1, 2, 3, 4, we have this very sharp line that will be our slant asymptote. Let's plot the other asymptote, which is our vertical asymptote, which we discovered is at x equals negative 3. Okay, so I'm going to do that in red. It's a vertical asymptote right at x equals negative 3. Okay, when you have a slant asymptote, you will notice, well, if you think about it, if you have a vertical line somewhere as a VA, and I'll just draw another diagonal line as a slant asymptote, you have these kind of triangle shapes, like in here and in here. And generally, this is where the graph will go. I haven't really seen examples where it doesn't. So just kind of bear that in mind, that that's the typical location. But as you graph it, there are a couple other features that are going to have to be consistent with what you're graphing. We do have an x-intercept, and the x-intercept is at -2, 0. Where is that? I'm going to plot that right here in green. It's going to touch there. And there's also a y-intercept. Where is that y-intercept? It's going to be on the y-axis, a little higher than 5, 5 1/3 to be exact. So I'm plotting it right there in green. So kind of the typical, hello, yep. The typical way a graph will look like is it'll come down, and you know what? It's going to bounce there. I'll explain that in a second, and come back up like that. Why is it going to bounce there? Look. Because you have x plus 2 as a factor in the numerator twice. You could express that this way as well, couldn't you? Right? And we know the characteristics of a factor that has a power of 2. There's a bounce. Had there been a power of 3, this would be a wiggle. But once, it's a cut through. The power of 1 is a cut through. In any case, that's the graph. Well, what you're not seeing here in this case is the graph skips -2 as you move from right to left. It skips -2, but continues right here. And conversely, as you move from left to right, it will not touch, it will do everything it can not to touch x equals -2, since that's a vertical asymptote, but it will continue after, which is way up here, after x equals -2. But to go over the main points, create a factored version if you're not already given one. Create a factored version of the function. Okay, this is really key. Then I would really have off to the side your 5 main characteristics, knowing that if there's no horizontal asymptote, because the degree is heavy on top, you might have a slant. Then I would plot the asymptotes first, and then a hole if you have one. And we didn't talk about how to calculate the hole, but I think you've had practice with that, as well as your x-intercept and your y-intercept. Then, with those features there, try to logically connect the graph in a way that makes sense, that is logical.